For the purpose of your physiology course, you should gain an understanding of the electrical and ionic basis for the ECG, or electrocardiogram. You should be able to identify and explain a normal rhythm from an anatomical, ionic, and physiologic purpose. We were previously introduced to the ionic basis of a heartbeat and covered the components of the QRS complex, but if you were to record a 12-lead EKG on someone in the emergency room who presented with chest pain, you would realize that not all the QRS complexes look the same across the sheet. When you couple all the depolarization and repolarization events throughout the cardiac cycle and take cutaneous electrodes to trace the activity between 2 points outside of the cell, you get the readout printed on the EKG machine that you see before you. All of these different leads are essentially different viewpoints of the same heartbeats. Let's take a look at the ECG paper. It has time on the x-axis and electrical activity on the y-axis. The paper is divided into small and large boxes. The small boxes combine in a 5-to-5 pattern to make a large box. Each small box vertically is 0.1 millivolts or 1 millimeter. Each small box horizontally is 0.04 seconds, which makes the big box 0.2 seconds. This is the standard format that you will see in the United States, but just realize that certain places may need to manipulate the paper speed or size for a purpose. The key to understanding today's lecture on vectors is to understand what happens with a single depolarization event among cells using 2 detection electrodes. We are going to take these 2 electrodes and assign one to be a positive and one to be a negative, and put them outside of the cell. As the cells on the left depolarize or become more positive, they send a signal that is received by the positive electrode. The depolarization events propagate down the line via gap junctions just as they would in your heart. When we read the printout from the ECG lead, we see a positive deflection. That's the key. A depolarization in healthy tissues towards a positive electrode gives a positive deflection. While the cell is finishing depolarization, the charge difference reverses and sends the reading back towards baseline. If a group of cells were to depolarize away from the positive electrode or towards the negative electrode, then the ECG machine would show a negative deflection that then returned to baseline. Interestingly, if a depolarization event occurred perfectly perpendicular in either direction to one of the electrodes, then there would not be a reading and the ECG would record a flat line. ECG tracings are dominated by 2 factors: the direction of the depolarization event, which is known as the vector, and the mass of the cells within the depolarization event. The more cells or more mass within the depolarization event, then the stronger the deflection will be recorded on the ECG tracing. I hope this will make sense using an example. So let's take a negative and positive electrode and show that we have a depolarization in the direction of the green arrow. That gives us this ECG tracing shown in red. However, what if the vector or direction of depolarization was this green arrow? Both positive electrodes see a depolarization event that travels towards it, but the direction of depolarization in example 1 has a more direct path towards the positive electrode, whereas the depolarization in example number 2 is at an angle to the positive electrode. The one with the more direct view is going to be the one with a stronger deflection. So now that we've been introduced to these principles, let's see how to apply these when taking a 12-lead ECG from a human patient and applying vector analysis. We first need to understand classical electrode placement. Electrodes are placed on the patient's extremities or close to them. From here, the machine assigns a positive or negative value to each electrode. The standard combination gives rise to the traditional leads that we read on the EKG printout. Think of a lead as a certain camera angle. We need to move to the right vantage point to get the perfect shot. In cardiology, we have to move to the perfect angle to get a picture of the right orientation of the heart. Lead 1 is made up by making the right arm lead negative and the left arm electrode positive. We assign this electrode a 0-degree designation, and we will fill in all the other leads based on this 360-degree orientation around the heart. Lead 2 is made up by a negative right arm electrode and a positive left leg electrode. Lead 3 is comprised of a negative left arm electrode and a positive left leg electrode. Together, these bipolar limb leads make up Einthoven's triangle. This is an equilateral triangle which sets up the basis for the rest of vector determination. From geometry, we can fill in the other leads' vantage points. Lead 2 is at positive 60 degrees, and lead 3 is at 120 degrees. Augmented leads take a single viewpoint and two negative electrodes that are combined as a single reference point. This gives us a perpendicular reading to one of the bipolar leads we just learned about. So lead AVF is the perpendicular pair associated with lead 1, which means that its vantage point is 90 degrees away from lead 1. This gives it a positive 90-degree view of the heart. People remember AVF as it points to the feet or the floor. The other two leads points to the patient's shoulders. AVL is the perpendicular pair to lead 2, giving it a vantage point of negative 30 degrees. When you see AVL, think pointing towards the patient's left shoulder. Lead AVR points to the patient's right shoulder and is perpendicular to lead 3. This viewpoint is in the complete opposite direction of the normal depolarization events and should be negative in a normal heart. Doing a vector analysis allows us to assess the conduction system of the heart. We're able to deduce what direction the myocardium is depolarizing, if there's an abnormal pathway, or if there's a thick myocardium that produces a greater voltage than expected. If we were to take the normal conductive pathway that we discussed before, beginning in the SA node and ending in the ventricles, then we would see the bulk of the depolarization starting near the patient's right shoulder and heads to their left leg. This is practically the lead view given by lead 2. So, if we were to see a tall positive deflection in lead 2, then we would think that the bulk of the depolarization within the conductive system is towards lead 2, or 60 degrees. This falls within the normal range. During class, you will discuss the normal values and even pathological changes that can be assessed via the ECG. Thank you for watching, and good luck with your studies.